All right, today we're going to start Chapter 2, Section 2.1 is titled Functions. And to start with, we're actually going to take a look at what a definition of a function actually is, and then some graphical inputs or information as well about them. So to start with, a function is a rule that assigns each element in one set to a unique element in another set. The input is the first set, which means that the output would be the second set, yeah. Likewise, you'll sometimes hear this phrase is independent variable or dependent variable. Independent variable is the one you choose. It's actually the input. We'll also call it the domain. And in particular, most of the time we use the variable x. And then the dependent variable would then be the output. Does anybody remember what the output is called? If the domain is the input, what the output is?
Range.
It's range, right. And again, for the most part, we call this either y, or we're going to have a new notation for it here in a moment. I'll write it in here as well, which is f parenthesis x close parenthesis. So the part of this that's really important is that each element is assigned to a unique element afterwards. So in other words, we can't take one element and give it two output values. That's not okay. Each element has a unique output value. So some context situations are functions and some aren't. For example, and this is me just thinking, actually, this is my first example. It's mailing of a letter. Everybody have this part written down, okay? Okay. C is the cost of mailing a letter, and W is the weight of a letter. Have you ever mailed a letter? Have you ever gone to the post office, bought the stamp, put it on the package, or sent something UPS or something like that? This is the idea. The question is C a function of W? Is W a function of C? Both or neither? Okay, so let's identify what each of these are again. C is the cost, right? It's the dollar amount. W is the weight. In pounds or ounces, whatever you want to use. I don't care necessarily. I guess if you're talking about a letter, you're probably looking at ounces. So if you go to the post office and you give them your letter, okay, do they have a unique amount of money that it will cost to mail the letter? Yes, as long as you're not saying, oh, I want it to go media mail, or oh, I want it to go first class or second class, or oh, I want to put, the tracking on it or whatever. All those sorts of things are add-ons. But the cost of it is actually a unique value. You give them the letter, they tell you it costs 54 cents to mail it, or it costs 92 cents to mail it, based on weight and these sorts of things, right? So the letter, the weight of the letter itself, has a unique price that it costs. So we would say that C is a function of W, the weight, because there is one price for the weight, right? The weight itself determines one price of the letter or the package or the whatever we're mailing. This one said older, I think. So what if we do the other way around? What if we said W, the weight. Is the weight a function of the cost? In other words, if you go to the post office and you say, hey, I see that somebody mailed a 54, is it 54 cents? Does anybody even know? It's 50 something, 51, 52. It's not 50 anymore because that was too easy. Does anybody know? I don't remember. It's been a little bit since I bought some stamps. So let's say 52 cents.
Stamps?
Yeah. Do you know what a stamp cost is right now?
I would imagine.
Is it 55? Yeah. Okay. All right. I've got Jamie for 55. So we'll go with 55.
Why is stamps so expensive?
I don't know why it's so expensive. I remember 25 cents is the cheapest I remember. That's giving you some of my age, I guess. 25 cents. Yeah. Okay, 55 cents. Thank you so much, Jamie. I knew it was more than 50 because it changed. 50 was just easy to buy stamps at. All right, so 55 cents. So if you go to the post person at the post office, you say, hey, I see that you put this stamp on it and it was 55 cents. Do you know for sure what the weight of the letter is? Doran says no. You don't, right? So in fact, you probably have had this experience before where you're thinking like, how much can I cram into this thing before they're going to make me put 2 stamps on it? Have you ever had that experience? Do you guys ever mail anything? Guessing no. Email. Well, I know I do email too. But we actually mail some things over to Ethiopia for our sponsor kits in Ethiopia. So that's my mailing for the most part these days. So I want to know how much I can cram in before they're going to make me pay more money. So I know I can do 1 piece of paper. I know I can do 2 pieces of paper. Once I get to 3, I'm starting to go, is it a little too heavy? I don't know. Maybe I can, maybe I can't. And I may go to the post office and let them weigh it to decide. Or I have a food scale at home. I might decide I'm going to try on my food scale and see if it'll weigh it that much, right? Okay. So you don't necessarily know the weight of the package just if you know it costs 1 stamp to mail. There's a range of values that all cost 1 stamp. And then there's a range of values that all cost the 1 stamp plus the extra ounce too, actually. And they keep going up like that with all of your packaging. So yeah, this doesn't actually work this way. So W is not a function of C. Because at a given cost, there is not one specific weight. That's the problem. There's not one specific weight. So if we go up to the question and it says, is C a function of W? That one was yes, right? Is W a function of C? And that one is no. So then we don't have to worry about the both or the neither because we've answered each individually. They could both be yes and then it'd be both. They could both be no and they'd be neither. Okay, any questions on that? Okay, so sometimes when we're looking at functions, we're not necessarily looking at specific values. We're looking at context. Does the relationship hold? Right? Does the relationship hold for it to satisfy? We can also look at graphs. How many of you have heard of the vertical line test before? Yeah, I've seen some nodding heads, raising hands. You probably have seen it, even if it's not ringing a bell at the moment. The vertical line test is actually a way of checking to see from a graph whether or not we have a function. So a graph will represent a function if and only if no vertical line crosses or intersects the graph in more than one point. I'm going to draw some examples here. Go ahead and write that definition down. So the idea is that we sort of drop these vertical lines through our graph and we check, does it cross it once or does it cross it more than once? So I have 3 graphs to draw for you. That's my first one. The second one. And the third one. They're sketches. Don't judge my artwork. I don't draw. Okay, so after you've sketched roughly the same pictures that I have, what we're doing is we're going to try and drop vertical lines. So we'll start with A. If I draw vertical lines through this, these look approximately vertical. question is there ever a place where I cross the graph twice or more? Twice or more than twice? No. Every time I drop a vertical line, I'm only going to intersect this particular graph one time. One time here, one time here, one time here, one time here, one time here. I'm always crossing it just once. If that feature holds, I have a function. So this one is a function. And here's why. Each input, namely each x value, corresponds to exactly one output, namely one y value. It's the dot that I've plotted. For every plot that I made, it represented an xy ordered pair, and that specific x value had that specific y value it corresponded to. What's going to happen on B, though? Yeah, there's going to be lots of places where it crosses it twice. Now, notice there's some places where it doesn't cross it at all. And that would be okay. There's nothing wrong with that, okay? But what is wrong is all these places where I cross the graph more than once. So this is the problem. What that means is that at this x value, right, because this vertical line is representing whatever that x value's distance away from the y-axis is, right? That's what it is. This is a distance from the y-axis. There are two y values, namely the one that's above the x-axis here and the one that's below the x-axis. So each input, x, does not have a unique output. It has two. So this one's a problem, not a function. What about on C? I run into the same problems, right? At least there are places where, didn't draw that super far in. Let me just shift it over a little bit so it's easier to draw my points on it. There are places where, when I draw a vertical line, it crosses my graph twice. And I have the same problem that I had in my circle. There are x values that have two output values that correspond to them. Thinking back to your circle, we actually worked a little bit with circles back in chapter 1. And if you remember, this happened, what we saw happening here was that we had x squareds and y squareds in our equation. And so the reason that happened from a logistical standpoint is that when I square things, then positives and negatives both become positive, right? So that's what's happening in terms of my output values, giving me two options. So this last one also not a function. Now, if you get a little bit more broad, there's actually something that correlates x's and y's together that doesn't actually have this extra condition of this every input has only one output. And that's actually called a relation. So relation is just a set of ordered pairs. Okay? They could be all connected, like the graphs we just did. They could be a verbal description, like our cost of mailing problem. Or they could be a list, literally, of ordered pairs. Okay? So that's what we have on this slide, is just lists of ordered pairs. These are relations. They might be functions, they might not, but they're relations. So we're going to decide from a point, like ordered pair points standpoint, whether or not we have a function. So if we go back and we think about the definition of function from this perspective, it says, I promise I'll go back to the slide, each element in the input should correspond to one output. So what I want to identify are the inputs. What are my inputs? I'm going to draw this out just so that we can see it a little bit differently. What are my inputs for number 3? 1?
0, 4, 9.
Fabulous. So the x values, right? 1, 0, 4, and 9. What are the outputs? 7 and 6, there's only 2 of them, right? So the input 1 corresponds to 7. The input 0 corresponds to 7. The input 4 corresponds to 6, and the input 9 corresponds to 6. They double up. The question is, does every input value have only one output? What's the output for 1? 7. It has one output, 7. What's the output for 4? 6. It has only one output. What's the output for 0? 7. It has only one output. What's the output for 9? 6. It has only one output. Each input goes to only one output. Okay? So this one is a function. Now, if you thought about graphing these, you don't necessarily have to draw this, but let me just draw this one for you so you can see why it works from that vertical line perspective. 1, 7 is something like this, right? 0, 7 is something like this. We have 4, 6 is somewhere like this. And 9, 6, I don't know, it's out here somewhere like this. It's just 4 dots. But if I drew vertical lines everywhere, most of my vertical lines wouldn't even hit the dots, right? And if it did hit a dot, it would only hit one dot. Every vertical line will only cross one of those dots once. So if you want to think of it from a vertical line perspective, you can do it that way too. Different things are going to happen then on part B, or number 4, I guess, number 4. What are my inputs on number 4? 7 and 6. And what are my outputs? 1, 0, 4, 9. Is that okay? Yeah, I just switched them, right? Hopefully you can see the relationship just did switch the order. The problem here is that the number 7 as an input has an output of 1. The number 7 as an input has an output of 0. The number 6 as an input has an output of 4. The number 6 as an input has an output of 9. So every input, and I don't even need every, I just need one. We'll take the input 7. If I have the input of 7, how many outputs do I have? 2. There are 2 here. And it fails twice, right? I mean, it fails for the 7 and for the 6. But even if it just failed for the number 7, it would be enough. This fails. This one's not a function. And if we took the graph of this one and we sort of plotted them, again, I'm just going to sketch them real quickly. I have 7, 1. So 7, 1 would be somewhere like this. I have 7, 0, that's right here. I have 6, 4, which would be like right here. And I have 6, 9, which would be like right here. And what happens if I try to drop vertical lines here? There's at least one place that, yeah, it crosses through 2 points, right? And in fact, on this one, there's 2 places where it crosses through 2 points. So you have a couple of different ways of thinking about this. You can think about it from at least 3, actually. You could think about it from a graph, right? Just plot the points and see what happens. Think of vertical line test. You can think about it from like an input-output type of a diagram, right? These arrows. I can't have an arrow coming from to a number and going to 2 different numbers over here. Or you can think about it as a relationship and ask yourself the same questions that I've been asking out loud. What output does this have? Does it have more than 1? And you can think from that perspective. So, did I already get that one? I did. Okay. There is, let me see if I have it in my notes. I don't think so. A really good verbal description of one of these where it works in one direction and doesn't work in another direction is if you think about biological family. Okay? So if I give you, every single person in here, you have one and only one biological mother. Agreed? But your mothers may not have one and only one biological child. Right? So in one direction, it works as a function. Every person has one biological mother. But in the other direction, it doesn't work. Every mother may not have only one biological child. So that's an example of one sort of verbally that has a the ability to not do an inverse. You can't switch the order around and it still works. All right, so we mentioned a moment ago the words domain and range. We identified that domain means the x values, and we identified that range means the y values. And so we're going to go back and we're going to look at these specific examples, namely 2a and then 3, for the domain and range. So I'm going to just flip back on my screens. If you just want to flip back in your notes to find 2a, then we're going to identify the domain next to it. So flip back to 2a. This was my graph, right? The one that's got all the yellow lines drawn through it. Domain, from a graphical standpoint, means that I'm going to move from left to right because we read from left to right, okay? Start on the left side because it's the negative side. We move to the right side because it's the positive side. And we're asking ourselves, what x values do I see? So if you imagined that I was on the left-hand side of this graph, right? I'm over here, and I'm moving through the graph as I walk, all right? And I'm looking up and down. So I'm kind of like walking along the x-axis. Walking along the x-axis, and I'm looking up and down. I'm going like this. I'm trying not to get dizzy, right? Okay, up and down. The question is, what x values do I see? Or what parts of the graph? Where do I see parts of my graph? And on this one, no matter how far left I go, in this case I'd be looking down, will I see part of my graph? I will. That's what this arrow here is supposed to be representing, is that this continues down forever and left forever. Now at some point here, I start looking up and I see parts of my graph, right, instead of down. And I keep moving and I look down and I see parts of my graph. And I keep moving and look up and I see parts of my graph. But from the left-hand side all the way to the right-hand side, I have parts of my graph the entire time. So my domain for that one is all real numbers. I always see values from the far left to the far right. And there are several ways that we could write that. So the domain for that, one way to write that is to just write out the words all, that is yellow, all real numbers, very bright. Let me change that to white. Another way to write that is that you could write, there's two other options actually. You can do an R with two lines on the left. That's actually the symbol for real numbers. A third option is to do interval notation, which we've talked about in class. It says that we go from the far left, which is negative infinity, to the far right, which is positive infinity, and we include everything in between. So there's several ways to write the same information. Next, we're going to look at range. Oops, too far. Okay, so my domain is moving from left to right, from the negative side of the graph to the positive side of the graph along the x-axis, right? My range is climbing a ladder. So again, I'm going from the negative part of the graph to the positive part of the graph. So if I'm climbing my ladder, I actually start on the bottom. So you're imagining that you're on the bottom of this graph and you're climbing up the ladder, okay? So when I was walking along the x-axis, I looked up and down, tried not to get dizzy. As I'm climbing up the ladder, I'm looking left and right. Definitely trying not to get dizzy and fall off my ladder. All right, so I'm going up my ladder, right, looking left and right. So because of these arrows going downward and upward, at the very bottom, if there is really a bottom of my graph, as far down as I start, I always see values, right? Because that arrow goes down forever. Now, at some point when I'm climbing up my ladder, I do encounter a place somewhere here in the middle where I look to the left and I look to the right and I see values in both directions. That's okay. There's nothing wrong with that. It doesn't change anything. The point is I see values. And I keep climbing up, and eventually I stop seeing the duplicate values on the left and the right, and I only see the values on one side or the other, and namely on the right as I get high enough up. But again, the arrow points upward, so as I keep climbing up, I'm always seeing the values to the left and the right. There's no place that there's a gap. I don't have something on this graph that looks like, a blank spot where I stop seeing values and I keep climbing and then I start seeing them again. I don't have that, right? I have a continuous, smooth place that I always see values as I'm looking to the left and the right. So on my range on that one, it actually looks just like the domain. I also have all real numbers. And again, you can write that as the double-blind R, or you can write it in interval notation. Just make sure you're doing whatever my math lab asks for in a specific problem. But as far as I'm concerned on a quiz or a test, I don't care which of those forms you use. Okay? Any of those are fine. Okay, does that make sense on that one? Okay, so that was from the standpoint of looking at a graph. Now on number 3, we don't have a graph. We have a list of points, right? Okay. But you know what? A list of points is easier. Because the domain are the which one? X's or Y's? They're the X's, and the range are the Y's, and that's exactly the numbers got written down, right? Like even in the input-output diagram that I made. So looking at that, whoops, sorry about that. My domain is simply a list. So I'm going to do a curly brace, and I'm going to list all the values. So what values were in my domain? 1, 0, 4, 9. And you can put them in any order you wish. Usually smallest to largest kind of makes the most sense. But it doesn't really matter. Those are my domain values. And then the range are the Y values, right? And what are my range values for this? Yeah, 7 and 6. Again, in either order. I'm a little OCD, so I do things in smallest to largest. Whatever is fine with me. 6 and 7. Those are your range values. That's it. Okay, so from a list of points perspective, we're just listing the X's and we're listing the Y's. And then number 7 actually is an equation, right? We haven't done an equation yet today. We've seen some graphs of them, but we haven't actually done one with an algebra equation. So taking a look at this, I do have a radical, right? And aside from section P7, where we worked with what happens when we have negatives underneath radicals, do you remember what happened in P7? What did happen when we had negatives underneath radicals? We pulled out i's, right? It was imaginary. We had the imaginary component. Well, when we're looking at the domain and range, we're looking at things inside of a real number system. So we're not going to let ourselves have the negatives underneath the radical because we're not working with the imaginary numbers right now. We're only working with real numbers. So what that tells you is that the things that are underneath the radical, they can't be negative for this to make sense in the real number system. Nod your head if you're good with that. Okay? In other words, what I just decided is that this 5 minus x has to be greater than or equal to 0. Because that's what's underneath my radical, 5 minus x. Whatever's underneath there has to be positive. So that's cool. I should be able to solve this. We did a section on that, right? Inequalities back in 1.7. I think it was 1.7. So what do I do first to solve this? What's wrong? Oh, hang on just a second then. Okay, after that brief moment of reconnecting, what would I do to solve 5 minus x is greater than or equal to 0? Subtract the 5 first. So now I have negative x is greater than or equal to negative 5. Now what? Divide by negative 1. What do I have to remember when I divide by a negative with inequalities? Switch the sign. Good. So now this is x instead of being greater than or equal to, it'll be less than or equal to what? 5. Okay, so this is telling me that my input values need to be smaller than 5. So like I can input a 4, but I can't input a 6, right? That's what that's telling me. Now the cool thing is that this right here is exactly your domain. You're done. So what are you going to do? Well, we're going to write that out. So my domain. And I'm going to show you a notation. I don't think I've shown this class yet. I think it was a different class that we worked on it. And so the domain notation is that we're going to put an X. We're going to do a vertical line. And then we're actually going to say X is less than or equal. Sorry, greater than. Yeah, no, less than or equal to. That was right. 5. This is called set notation. This is actually telling you that your domain is all X's. This vertical bar means such that. This is saying X is less than or equal to 5. It's just a notation. You can also do an interval notation for this, right? So if it's less than 5, that means that it would be from negative infinity up to 5. And now I'm going to use a parenthesis or a bracket. Bracket. So you could use interval notation for that. Okay, let's think about range. What in the world would be the range of this guy? In other words, what y values are you going to actually have sort of come out of this function? And what are you not going to have come out of this function? If I put in x is equal to 1, what do I get? 5 minus 1 is 4. Square root of 4 is 2. Okay, so we get a 2 out of it. What if I put in x is equal to 4? Yep, I'll get a 1 out of it. Is there anything that I absolutely cannot get to come out of this function? A negative, right? No matter what numbers I put in, when I take the square root of them, I'm taking the principal or the positive square root. So I always get positive numbers come out of this. What that tells me is that my range is all y values where y is greater than or equal to 0. Or if you want to use interval notation, this would be from 0 to infinity. And yeah, you can get 0. If x is equal to 5, which it is allowed to be, right? X could equal 5. If x is 5, then the square root of 5 minus 5 is 0. So you get a square root of 0. 0. That works. So this is a domain and range. Any questions on that? Okay, our last place that we're going to pause for a little while here today is going to be function notation. We're going to do a few examples with different things with it, but we're talking about notation now. So I mentioned this notation earlier. Function notation looks like a name that's often an F, G, and H. Those are, for some reason, the typical ones. People use F, G, and H. You can use anything, but F, G, and H are really common. And then there's a parenthesis next to it with an X inside of it, and then it equals something on the other side. Now, the first thing that I want you to understand is this is simply another way of writing y equals x squared. That's what it means. Okay? Okay, so you're like, well, then why have that notation? Well, it has some really nice features that y doesn't, and that's why. So the first thing I want you to understand is that those parentheses do not mean multiply. This is not g times x. Parentheses are probably the worst convention of mathematics because we use it for multiplication, we use them for grouping symbols, we use them for intervals, and we use them for function notation. That's ridiculous. It just is. So it doesn't mean multiplication here. What it does mean is it means that your function has a variable x. That's all it's telling you. So this notation is just saying my function's name is g and the variable is x. And we read it as g of x. All right, that's how we think about it. So what happens down here, and this is why the notation is kind of friendly, is you see on the second one here a 2 in the place of where the x was, right? I now have a 2 here. Previously it had an x, now it has a 2. So what it's telling you is put x equal to 2. So we do that. 2 squared. So it's sort of concise notation of saying y equals x squared. Now let x equal 2. I just say g of 2. And we would solve it, of course, and that would be the number 4. Likewise, on the next one, g of negative 2. Well, we do need to be a little careful when we're dealing with negatives, that we remember it's the negative 2, not just the 2 part of it that's being squared. So negative 2 times negative 2 would give me another 4. And there's nothing special about 2's and negative 2's here. I could choose any number. So if you wanted to find g of 7, okay, we can do that. G of 7. We just replace the x with 7. We can do fractions. We can do decimals. We could do g of pi. Pi squared. Okay, so there's nothing special about the numbers that are being plugged in there. Our second one here, number 9, is a little bit more complicated because it has 2 variables. Well, let me back up. It has the variable x, but it's located in 2 different places, right? So I have 3x squared, and I have minus x. So my function name here is actually f with the variable x. So on the first example, f of 2, it's asking us to, again, replace all the x's, now I have a couple of them, with the number 2. So I have a 2 in the place of the x here, and I have a 2 in the place of the x here. Okay, it's just an evaluation step. Okay, something else to remember is that when this says 3 times 2 squared, order of operations tell you what do you have to do first, the 3 times or the 2 squared? The 2 squared. Okay, it's easy to sort of move from left to right and forget that piece. 2 squared, order of operations. So 2 squared is 4 times my 3 would be 12. Now I have 12 minus 2 to give me 10. The last one on this slide looks sort of funny. You're like, well, there's a w there now. What do I do with it? You literally just rewrite it with w's in there. There's no simplification. So now it's 3w squared minus w. That's all. All right, so we're going to use this function notation in this is the last topic. If I have time for 2 examples, I'll do 2, otherwise I'll just do 1. Our last topic for this section, we're going to use this notation, and this is called the difference quotient. So let me actually write out for you what the difference quotient is up here in this sort of black header space. It's f of x plus h minus f of x over h. That has a name. It's called the difference quotient. Every time I teach this in college algebra, it feels like it's this sort of weird add-on piece that doesn't really have a lot of connection for you at the moment. And that's actually kind of true. But it is used in future mathematics classes, depending on where your mathematics leads you. I know for many of you this is the last place that you're ending in your math, but not for everyone. So this difference quotient becomes really super important in further math classes. That's why it's so special that we mention it here, just as an FYI. There's lots of ways I could teach this, and I don't even think I'm going to teach it the way my notes are, actually. So I want to teach you a 3-step process. Are you cool with that? Okay. I think it helps people to see what's happening in that sort of expression if I do it in 3 separate steps. But here's the condition. If I do it in 3 separate steps, you have to label them 1, 2, and 3. So I need to know that what you're saying is that I'm changing from step 1 to step 2, and I'm changing from step 2 to step 3, and not just like strings of equal signs of things that are not actually equal to each other. So here's step 1. And I'll label what they are. You don't necessarily have to write what they are on your homework or anything. But step 1 is to find f of x plus h. So what does that mean? Well, I'm given a function over here. It's 3x squared plus minus x plus 7. Okay. Back on this problem over here, when I had the w, I said, yeah, it feels kind of funny. We're just going to rewrite the w in the place of the x, right? But that's what we did with the 2, isn't it? Just put a 2 in the place of the x. Well, I'm going to put an x plus h in the place of the x. All of it. So I have a 3, and I have an x plus h squared. I just replaced x with x plus h. And then I have a minus, and I have an x plus h inside a parenthesis because it's all replacing the x. And then I have a plus 7. Have to clean up the algebra. Okay? So, still inside of step 1, I need this to be x plus h times x plus h. And then I'll go ahead and distribute this negatives. This is minus x minus h plus 7. Okay, so we have 3 things multiplied, a 3, an x plus h, and an x plus h. It's easier to multiply the 2 x plus h's together and the 3 last. You'll get the same answer either way, but that's the easier of the 2 steps. So this is x squared. My inside and my outside are both xh. So that's plus 2xh. And then my last terms are h squared. And you have this. So the last part of step 1 is to distribute the 3. 3x squared plus 6xh plus 3h squared minus x minus h plus 7. Step 1. Step 1 is the hardest step. It's the messiest step. Okay? Everything else in step 2 and step 3 are going to make things disappear. It's like magic. You ready for some magic? Okay, so step 2 is to subtract f of x. So literally what I've got here is I have the f of x plus h that I just found, and I'm going to subtract f of x. Well, the f of x plus h that I just found was 3x squared plus 6xh plus 3h squared minus x minus h plus 7. That's the first piece, right? And then I'm going to subtract f of x. Well, f of x was what I was given. It's the 3x squared minus x and plus 7. Now, if you really want to distribute the negative through here, you totally can. But I'm going to tell you it's not necessary, and here's why. Everything in the second set of parentheses matches with something in the first set of parentheses to eliminate it. Everything. So here I have a 3x squared, and here I had a 3x squared. And here I had a negative x, and here I have a negative x. And here I have a 7, and here I have a 7. And lo and behold, 3 pieces disappeared. And what I'm left with then is 6xh plus 3h squared minus h. It's better than it was before, isn't it? Not only that, but everything has an h in it. Do you see that? It's really important because you know what step 3 is? Yeah, basically, it's divide by h. So I'm going to take f of x plus h minus my f of x that I just found and write it on top of an h. So 6xh plus 3h squared minus h, divide by h. And I'm able to cancel, eliminate, reduce, divide out, whatever words you want to use. This h, one of these h's, and this h, cancel with this h. Please be careful. The h in the numerator that I just canceled, that was minus h. That's now a 1. It's not a 0. H divided by h is 1. So I have a 1 right here. So my grand result of all the work is 6x plus 3h minus 1. I will record the last one problem. If you would like to look at another example, it's just going to be another example of this. So if you feel good with this and you don't want to watch my last 5 minutes or whatever of another example, that's totally fine. But I'm going to go ahead and just keep this rolling when you guys leave. I'll pause it for now. When you guys leave, I'll just record the last. And if you want to come back in and watch the last 3 minutes in order to get the last example, you can. Have a great day. All right, and as promised, the last example for those of you who wanted to check back in later and see one more problem of these difference quotients. So you'll notice on this one that we have a similar equation to the last problem, and we're going to do that same 3-step process. So the first step is to find f of x plus h. And just for clarity, I'll use g because this problem starts with g. So we'll do g of x plus h. So everywhere I have an x, I'm going to replace it with x plus h. So I have x plus h squared minus, the quantity is x plus h, and then plus 3. So just like on the last one, I need to clean this up, simplify the algebra. I can distribute the negative through, so minus x minus h plus 3. And then my first terms here is x squared. Inner and outer are both xh's, so I have plus 2xh. My last one is h squared minus x minus h and plus 3. Okay, and that's actually step 1. Step 2 then is to take that same g of x plus h I just did and subtract g of x. So remember, labeling your steps. That's what I'm going to expect to see on your homework if you decide to do this in a 3-step method. So we're going to have that same piece I just found, x squared plus 2xh plus h squared minus x minus h plus 3. And we're going to subtract the original g of x equation we were given, which is x squared minus x plus 3. Again, if you wish, you may distribute, but again, all those pieces are going to pair up. X squared and x squared, negative x and negative x, 3 and 3. Like magic, 3 pieces of it disappear just like that. And I'm left with 2xh plus h squared minus h. And then step 3 is to actually take the quantity I just found, again, in step 2, which was g of x plus h minus g of x, and divide by h. So 2xh plus h squared minus h, divide by h. So h here would become a 1, so it's just 2x. H squared here becomes an h, and the negative h here becomes a 1, negative 1, and this h becomes a 1, so it cancels. And I'm left with 2x plus h minus 1.